Unit Operation Classroom. Today we are going to discuss average velocity from a parabolic velocity profile in slit flow. We'll discuss and try to understand what is a slit flow and what's parabolic velocity profile and how to calculate the average velocity. My name is Shekhar Bhattacharya. What's the problem? The velocity profile for a fully developed laminar flow of an incompressible, let's say liquid Newtonian fluid at steady state to a horizontal infinitely wide long slit of gap 0.01 meter. So this is a gap of 0.01 meter is given by this fall. So this is basically a parabolic velocity profile. So this is like a plus bx by squared, right? So this is a parabolic velocity profile where y is the vertical distance. We look into it from the center of the slit. So we have to find the average velocity of the fluid. So first let's try to understand. First let's look at the some kind of an industrial relevance of this problem. So this is like a slot die coating equipment here. So basically this is a slot. So here is this very thin, very small opening here through which coating liquids like polymeric solution, adhesive, etc. come and is deposited on the films. Okay, so here's a die head here. So, and this is a very thin slit through which this is a polymeric solution comes out, and this is, let's say, viscous Newtonian fluid and flows steadily through a long wide slit. Okay, so very strong long wide slit, and this is the adjustable gap of 0.01 meter according to this problem here. This is a 0.01 meter. Okay, so if we try to see a bigger schematic of this problem, so let's say this is my the gap here, this gap what we are talking about here. So let's give through which the polymeric liquid comes out. Okay, and this is the upper plate here. So this through which, and between these two the polymeric solution comes out. Okay, and so this is a flow between two parallel plates. So flow between two parallel plates here. Okay, and it's a parabolic velocity profile which is given as uy. That means u, that the velocity is a function of y. So let's say this is my center line here. This is my center line. Okay, and we measure the distance from this center line here. So here y is equal to 0, and as we go here, this, let's call this u is equal to 0.005, and this is equal to negative 0.5. Of course, the total distance is equal to 0.1. So this is 0, this is divided by 2 is of course plus 0.5 and negative of 0.005. Okay, so let's take a very differential strip at a distance y. So we're talking a very there's a small differential strip here. Okay, and so this is my center line. So let's see, the slit gap is 0.01 meter, what we have seen, and y is measured from the center line. Hence, walls are at plus minus 0.005 from the center line, which is this one. So this walls are at plus 0.5 and minus of 0.005. This velocity profile is given 7.5 minus this one. So this is like a plus by squared. It's a parabolic velocity profile, and as you can see at y is equal to 0, which is right here, the velocity is maximum, and as we go on this way and this way, of course the velocity will decrease. Okay, so we have to find the average velocity as it flows to here. What is the average velocity as it flows to this polymeric liquid flows between these two parallel plates. Okay, so how do you do that? You know, the average velocity is defined as, so here what is this is u as a function of y. This is just u as function of y. This is nothing that, so you can actually write this one as u dy basically, and to 1 of course dy. So how this becomes, see, if this is the velocity, let's say at this point at a distance y, this is my velocity u. Okay, as I said, this is uy, that means velocity u at a distance y from here. So what is the area through which it follows? So this is basically, if I take a unit width here, so basically as you can see, the area of the flow is dy. This is dy, this is dy into 1. Okay, so this, what is the flow rate to this one? So if the velocity is u, so the flow rate would be equal to u times dy into 1, because this is the area and this is the velocity is u, so it will be u times dy into 1, right? So that's what it is. So u times dy into 1. As I said, this is u as just a function of y. Okay, so if we integrate this one, if we integrate, if we take this differential section and if we integrate between this the plus 0.005 and negative 0.005, we'll get the total flow rate. So that's here, this is 1, that gives you the total flow rate. This is 1 plus h over 2 negative of h over 2. Okay, and so if this is equal, this one is total volumetric flow of the polymeric fluid through this one, and now we have to divide by the area, and this area of course is equal to, if this is h times 1, so that will give me the average velocity. So that's what it is. This is the total volumetric flow rate between plus h over 2 and negative of h over 2, and the area of the flow is h times 1. Okay, so next part, of course, this uy is given, this is a function of y is given. So next part is just very simple, do a little bit of integration, and these details are given here. So we see here, these are all given in this website. This comes as 5 meters per second. So as you can see here, this is where at the center line will be the maximum velocity, and of course as it touches the walls, right, at plus h over 2 and negative h over 2. So this is a no slip condition. Here the velocity u would be equal to 0, and this is also u would be equal to 0, right? Okay, so what are the checks? First of all, this is a parabolic velocity profile between the plates. So u max would be at y equal to 0. This is my u max here. This is here the max. Here's the maximum. So this is my u max. This would be equal to 0. So here this is equal to 7.5, because if you put y is equal to 0, this is going to be equal to 7.5. And at the walls, if you plus minus 0.005, this is a square here, so of course that will accommodate both plus and minus, so it becomes equal to 0. So this velocity profile, so this velocity profile satisfies the conditions right there. So this is the maximum, here it is 7.5, and here the velocity is 0, and here the velocity is 0, and this is a parabolic velocity profile. Okay, so for fully developed laminar flow between two parallel plates, the average velocity is, of course, we know is normally 2/3 of the u max, and that becomes equal to 5 meters per second, which we have got. So this matches our result. Just what are the key lessons and the takeaways from this problem? For a fully developed laminar flow through a slit between two parallel plates, velocity profile is parabolic, we have seen. Okay, whereby is the distance measured from the center line, okay, average velocity is obtained by integrating the local velocity over flow area. So this is, you have to forget that this is a volumetric flow rate divided by the flow area, so that gives you the average velocity. For laminar flow between two parallel plates, so this is 2/3 of maximum. Just for the sake of comparison, for fully developed laminar flow through a circular pipe, we know, again, this is a parabolic velocity profile. If you remember, this is a very standard, and we know u bar is equal to half of u max, and we know, we use the same thing. This is the total flow rate in the pipe here, and that is equal to u as a function of r. This means you can just write here u also. Just this means by u as a function of r, 2 pi r. The way we get it is here. Let's say here we take a differential section. So this is a pipe, and we take a differential section between let's say this is r, and this is r plus dr, or delta r, let's say. So we have to find the flow area between these two. So this would be equal to, so this is r plus delta r, and this is r here. So the flow area is equal to pi times r plus delta r whole square minus of pi r square, and that is equal to pi times r square plus 2 pi r delta r plus delta r square minus of pi r square, and of course these two cancel out, and this is 2 pi delta. This of course is small differential section, so basically this is 2r dr. So that's what we get here, and if you multiply it by the velocity, local velocity there, that gives you, and if you integrate between 0 and r, that gives you the total for it, and now that's divided by the total flow area, which is pi r square. That's the pi r square, that's the area of the flow of the. So finally the answer is of course u average is of course here is 5 meter per second. The average velocity is 5 meter per second.